All right, so we're going to talk about global climates and biomes. And one of the first things that we need to think about is the difference between weather and climate. So weather, short-term conditions, changes, on a day-to-day basis or certainly a weekly basis, temperature, humidity, precipitation, barometric pressure. Um, we experience weather not as often in California, but definitely, wind, changes in wind, temperature, and then obviously precipitation during the rainy season. Climate is a much longer term trend. So climate happens over, decades, and, different biomes on Earth experience different climates. You can describe, the temperate deciduous forest of the East Coast having 4 distinct seasons, with precipitation that can happen at any time, any of the seasons. Where we have here in Southern California more of a Mediterranean climate, and defined more by, a wet and dry season, where we have moisture, precipitation that happens during a few months of the year, and then typically it's dry for the rest of the year. That's our climate. So we want to look at all the dynamics that play into climate systems and sort of setting up the different biomes that we see on planet Earth. So looking at our atmosphere, we live in the troposphere. That's where most of the weather occurs, and it's the area that's between 0 and 10 miles from the Earth's surface. And then just above us, the next layer is the stratosphere. That's roughly 10 to 31 miles. And in between the two is what's called the ozone layer. And it's an area where ozone molecules accumulate. It's not exclusively ozone, but it is a higher concentration of ozone than anywhere else in the atmosphere. And we'll look at that. So several layers to the atmosphere. You have the troposphere, right? Stratosphere, mesosphere, thermosphere, and then the highest level of the atmosphere is the exosphere, which transitions into space. Proportionally, the atmosphere on Earth is as thin as the skin of an apple. So if Earth was to be the same size as an apple, our atmosphere would be as thick as the skin is of an apple. So our atmosphere is very thin relative to the total volume of the Earth itself. And you can see that when you look at Earth from space, images of Earth from space, the area that we actually see is defined in these pretty distinct layers, and here you can just make out the exosphere, the highest layer here, relatively thin, again, compared to the total volume of the Earth itself. Again, you can see the atmosphere here. When you compare density, our atmosphere is 100 times denser than the Martian atmosphere, which is kind of interesting. We have we just launched in July a probe that's going to Mars, and it should land in February of 2021. We'll be able to see the first flying vehicle on another planet. So this probe contains the Mars helicopter, and it's designed to operate in that very thin Martian atmosphere. Okay, we talked about the ozone layer. This is critical. This area of ozone density or increased ozone concentration is critical for filtering out UV radiation that's coming in from the sun. So UVB and C are effectively filtered out. UVB gets through in a small percentage, but these are filtered out by that ozone that absorbs that radiation, and that creates good conditions for us. If we didn't have that ozone layer, we'd have significantly higher incidence of skin cancer. So we're just really not evolved to be adapted for that radiation. Okay, unequal heating of the Earth. So, basically what we're going to look at here is the systems that are in place that create our weather or our climates, both really. So when we look at Earth itself, We're a sphere in space, constantly being bombarded by solar radiation. Of course, we're rotating, so we're being, uniformly radiated over a 24-hour period. And the equator gets radiation directly. And the polar regions of the Earth get radiation obliquely. So the same amount of energy hitting the equator might be distributed over 1,000 square kilometers, whereas that radiation that's hitting the Earth at the polar regions might be distributed over 2,000 square kilometers. So the amount of energy hitting the surface at the polar regions is less per unit area. Got that represented a couple different ways here. And so what that means, right, is that our equatorial regions of planet Earth are warm and our polar regions are cold, which we know. Okay, and when we look at Earth's energy budget overall, you can see, in general, incoming solar radiation gets absorbed by the land itself and the Earth's oceans, and then also re-radiated back out into space. And this has been, pretty constant for the last 10,000 years, since the last ice age. There have been natural fluctuations in the amount of radiation being trapped by Earth in our atmosphere, and then also at times, more radiation going about into space than we're holding on to, and consequently we enter an ice age. Okay, albedo is going to be the concept what we explore in the lab. So the idea of reflectivity of a surface. So overall, the average of Earth is about 30% reflective. About 70% of the energy coming in gets absorbed and turned into heat. Our clouds are variable in their reflectivity. Ice tends to be highly reflective, anywhere between 50 and 90% reflective of radiation. And then pavement is the other end of the spectrum. So that tends to be highly, absorptive or holds on to the radiation. So 90 to 95% of the radiation coming in will be transferred to heat. And so we get these urban heat islands where you have large amounts of the surface of the Earth being, paved or a built environment, and that tends to absorb, a lot of heat. Got a satellite going up. Actually, it's up and is giving us a much better understanding of both climate and weather on Earth, and giving us a really high resolution view of the greenhouse effect. And some of the data sets are starting to come in with that. But overall, we have this unequal heating, okay? And that creates these atmospheric convection currents. They're driven by just physical properties, density. Less dense air rises, and denser air sinks. Water vapor capacity. Warmer air tends to hold more water vapor, does hold more water vapor than cool air. You have this phenomenon related to that called adiabatic heating and cooling. So as air rises in the atmosphere, there's less atmospheric mass pushing down on it, so less pressure, and so that air expands. And expanding air mass holds less heat, cools off. Conversely, as an air mass sinks in the atmosphere and gets closer to the Earth's surface, there's more atmospheric pressure pushing down on it from above, more weight of all of the atmosphere above pushing down. And so that air mass will contract and take up less volume or space. And consequently, shrinking air mass, that energy occupying a smaller space, that causes that mass to heat up. Okay. And then finally, the idea of latent heat release. So when you have a precipitation event, you have condensation, and there's energy released with that condensation. And so, we experience that as, a rain event causing the temperature to drop, at least a few degrees. Okay, so those physical parameters set up these convection currents, and in the equatorial regions, we call them Hadley cells. Near the poles, they're called polar cells. And equatorial area, often called the intertropical convergence zone, It's where these two Hadley cells converge here at the surface of the Earth. So you have air running into this zone here, represented by number 1, from both northern latitudes and southern latitudes. And then that right over the tropics, that's going to be the most radiation. So you have these warm air masses rising and undergoing adiabatic cooling. So as they rise into the higher parts of the troposphere and ultimately the stratosphere, they cool, and then they're replaced by warm air coming in behind or underneath. And so that warm air rising pushes the cold air out of the way, and that cold air sinks. And as it sinks and comes back toward the Earth's surface, it undergoes adiabatic heating and gets drawn back into the ITCZ, the Intertropical Convergence Zone, where this cycle repeats. And you have these convection currents that are basically constantly in motion, sometimes stronger than others. And they sort of look like this. So you have these bands of rising air getting pushed out of the way and sinking and getting drawn back in, both north of the equator and south of the equator. And then you add in this idea of the Coriolis effect, which is the rotation of the Earth having an influence on these Hadley cells. So as the Earth rotates, there's a deflection of the air masses, and this is more intense near the equator because objects are covering, a greater distance than they are at the poles. Okay. So you get this kind of spinning or twisting effect on these Hadley cells. And ultimately, that's how we see the formation of things like, cyclones and typhoons and hurricanes. Okay, another physical parameter that's operating is the idea of seasonality. So our tilt, 23.5 degrees, has changed over time. It's not always been that, and it may change, it will change in the future. But that tilt causes seasonality. So, in our yearly journey around the sun, there are times where the northern hemisphere is tilted more directly toward the radiation that's coming in. And then as we're approaching winter now, we'll be tilted sort of away and receive solar radiation at more of an oblique angle. And that will sort of culminate at the solstice in December on the 21st. And then we'll start to tilt, as we go around the sun, our tilt will start